Hello and welcome to A Day in the Half-Life, the podcast about the past, present, and future of the science and technology that shapes our lives. This episode is all about hydrogen, because the smallest element in the universe has a lot of big applications. I'm your host, Aaliyah Kovner, and my guests today are two experts working to bring hydrogen technologies from development to real-world deployment. First up, we've got Adam Weber, a chemical engineer who studies fuel cells, batteries, and solar fuel generators. He is the lead of Berkeley Lab's Energy Conversion Group and Hydrogen and Fuel Cell Technologies Lab Program Manager and co-director of the Department of Energy Million Mile Fuel Cell Truck Research Consortium. My other guest is Hanna Brunig, an environmental engineer who performs modeling and systems analysis to study the social, economic, and environmental impacts of emerging energy technologies. She is deputy head of Berkeley Lab's Sustainable Energy and Environmental Systems Department. Welcome, Adam and Hanna.
Hello.
Thanks. Happy to be here.
Great. Thank you both so much for joining me. So let's dive right in. In this episode, we want to talk about clean hydrogen because we need the future to be powered by clean and sustainable energy. And we, of course, want to move away from polluting energy sources and our reliance on petroleum. So can you start by telling us what clean hydrogen is and how it's different from the other sources that I'm guessing are not so clean?
Sure, I can start with this. Basically, hydrogen exists in its natural form as a gas, but really that only exists on the sun. It doesn't really exist anywhere else on Earth besides some kind of form like water, where it's bonded with oxygen. And so when we talk about clean hydrogen, what we want is a clean way, so a way that doesn't emit a lot of CO2, a lot of other pollutants, to break those bonds and make hydrogen into a gas. And then we can do a lot of different things with hydrogen once it's generated. There are a lot of different ways to kind of break those bonds, whether it's a hydrogen-oxygen bond, whether it is a carbon-hydrogen bond in something like a fossil fuel. And so what we would call the less clean ways are things like taking methane as a starting gas and then breaking that because that emits CO2. And really what we want is ways to make hydrogen that don't emit any CO2 or other pollutants.
Mm-hmm. You might hear about the colors of hydrogen. So when we talk about green hydrogen, we're talking about using electrolysis powered by wind, solar, or nuclear electricity sources that have low greenhouse gas emissions associated with them. When we talk about gray hydrogen, we're talking about hydrogen from natural gas, as Adam mentioned. And for every ton of hydrogen, you emit about 10 tons of CO2 in that process.
Oh, wow.
If you're making hydrogen from the gasification of coal, that's brown hydrogen, and you're emitting about 19 tons of CO2 per every ton of hydrogen. Now, if you're somehow able to capture carbon dioxide emitted in those processes and sequester it, store it underground or sequester it in another form, that's called blue hydrogen.
I see. And what, at least in the US currently, would you say are the most commonly used types as of now?
Yeah, as of now, gray and brown hydrogen are the most common methods for producing hydrogen globally, including in the US. However, we're seeing a major shift in our understanding of what needs to be done to decarbonize the use of hydrogen. And we're seeing more and more dedicated systems for green hydrogen emerging.
Right. Yeah, there's a lot of movement in the hydrogen industry recently, I've heard, thanks in part to the Department of Energy Earthshot initiative, which calls for a reduction in the price of clean hydrogen, which, as you're both mentioning, would help get that green hydrogen more commonly used than the other forms. So that's a good thing. But we've been using hydrogen for quite some time as a civilization. The first thing that pops to mind for me is fuel cell vehicles. So how is hydrogen being used as of now with today's commercially available technologies?
Sure. So the beauty of hydrogen is that it's a way to interact with a lot of different systems and energy systems. And so the most common use of hydrogen today is in things like refineries to where it's being used to take, base fossil fuels and make them into something that we might put called gasoline or aviation fuel, and kind of upgrade. Similar to things like industrial processes, a lot of hydrogen today is used to make ammonia, which makes fertilizers.
Okay.
To use hydrogen, and so what I do here at the lab too is looking at making fuel cells. And so a fuel cell is basically an electrochemical engine. It is going to take hydrogen and create electricity from it, and then bring in oxygen and make water. And so what we see here in California specifically is the first market for fuel cell vehicles. This is primarily everything from passenger vehicles like a Toyota Mirai or a Hyundai Nexo that you can buy and fill up if there are stations, to things like buses and fleets. AC Transit has been operating in Northern California, for example, a hydrogen fuel cell fleet for a very long time, over 20 years, and we have a lot of interest from other fleets of buses. The key thing for hydrogen is really when we start looking at things like long haul trucking, things that have a lot of hydrogen demand, a lot of high energy, a lot of high power. Hydrogen seems to be a very nice way to do that in terms of the transportation network. And so what I like to say is hydrogen is replacing a lot of diesel engines, if you want to think of it that way. So when you have a diesel engine, we can replace it with a fuel cell that's run on hydrogen, only emits water. And so you're not emitting particles, you're not emitting any of the black soot or anything else that you might see.
So the trucks and the other sort of heavy-duty vehicles that might get hydrogen fuel cell conversion in the future, these are examples where just a simple electrification wouldn't work because of issues of distance. Is that correct? Like they need to go a longer duration than an EV engine could take them?
Sure. So the engines themselves will be the same. It's really just where it gets powered from. And so if we look at hydrogen versus a battery, so if you want to expand the range of a truck, when you do that with a battery, you have to multiply the number of batteries you have. With hydrogen, you have an energy generation source, which is generating your power, which is the fuel cell itself. And then you also have kind of the storage of the hydrogen, which is the total amount of energy in the system. So because those are decoupled, as you're going towards applications that require a lot of runtime or distance, the hydrogen starts to make sense on a weight basis. And so let's say a long haul truck can carry more cargo for the same weight and same distance with fuel cells compared to something like batteries.
Oh, cool. Thank you.
And I think there are a lot of also industrial applications. I think Hannah is much more familiar in a lot of those application spaces where hydrogen's becoming more important.
Yeah, and aside from industrial that we think about just the manufacturing, we also have applications on energy storage, which is going to be really key for getting more wind and solar, these intermittent renewables that don't operate every single hour of the day, but might need to serve demand for electricity that is going to be instantaneous, let's say backup power in case of a natural disaster. Or perhaps it's just going to be a steady demand of electricity from some community, like a hospital. Those kind of things need storage, whether it's a battery, a storage of the electricity, or storage in another form, such as hydrogen. In the case of hydrogen, we know that as you scale number of hours as well as power output, it's going to outcompete electric battery storage after about 12 hours of storage. So there's a sweet spot there where we really need solutions that can handle multiple days of intermittency on the renewable side. In addition, this is also really important if you're in industries that use hydrogen potentially as a feedstock. So that might be methanol production, or the new push to decarbonize iron and steel making is starting to think of hydrogen as a feedstock for reducing the iron ore. In those cases, you need hydrogen as a form of decarbonizing. It's a transition away from the use of coke or natural gas as a feedstock, providing both the heat and the reducing agent. So hydrogen can do that. There are early stage technologies for electrifying some of these industrial processes, but they're still very far away, and they're going to be taking electricity away from other end uses. So again, there's going to be a balance of how much wind and solar we're dedicating to different things and what's going to be the most efficient pathway.
I learned from the energy storage episode of this podcast about the large-scale energy storage application for hydrogen, which, as you said, could really help us transition to more renewables. So I'm just wondering, to get the electricity back out of the hydrogen, would this essentially be using giant versions of like the fuel cells we would see in a car, or is this something different? And are there any facilities doing this on a significant scale yet?
Sure. So, I mean, like I said, fuel cells are basically ways to take hydrogen and get electricity out of it and producing water. The nice thing about any of these kind of electrochemical technologies, whether it's a fuel cell or battery, is they're extremely modular and scalable. And so there are things of just stacking up fuel cells to, let's say, the megawatt type of power ranges or even beyond. And some of that is being done today by current fuel cell manufacturers. The other thing is you can also think of burning it in a turbine. So you can also burn hydrogen the same way you might burn natural gas. And so then you could use that for like aircraft engines,
Oh.
which are turbines, or very large power generation would be another way that we could do these with hydrogen.
Do you envision, there's other proposed things for energy storage for the grid, things like flow batteries. Do you envision the future would be sort of like a mix of these different technologies, or do you think that maybe one of them will emerge as the most efficient?
Hannah, do you want to take that one?
Yeah, sure, Adam, thanks. So each of these different forms of energy storage has its advantages and its limitations. That's why we've seen in the battery world, there are so many different chemistries that we've known about for a very long time. And there's still a lot of research going on many of them because there are issues around energy storage, power delivery, durability, weight, all these factors that come into play that you can't necessarily predict just from a chemistry itself. This is why we really think about team science in the energy storage world, because we need to understand how the different technologies may match to applications. As climate change is changing the needs of community members, there's going to be a willingness to pay for different aspects of batteries, hydrogen, energy storage that we don't fully appreciate in our current models. So we're seeing a really exciting period where we're starting to account for environmental emissions, social needs, as well as economic needs and technical performance in these systems.
Great, thank you. So this kind of flows nicely from that. I wanted to talk about, barriers to deployment, because these applications are obviously all sound great, getting rid of diesel engines and having our grid run on 100% renewables. And I feel like members of the public, and myself included, hear a lot about these technologies. I get the privilege of writing about them, which is quite fun. But, the natural question is like, well, why aren't we seeing them used on a larger scale yet? And I know we've sort of already been talking about that, but I'm just wondering, what are some of the main things getting in the way as of now that you are both kind of working to get around?
Yeah, so one of the main barriers for any new technology is cost, and really the cost of what goes into the infrastructure, the technology itself, and buying. Let's say a fuel cell truck today is not as cheap as a diesel truck,
Right.
and a lot of that has to do with manufacturing because a lot aren't manufactured, and so there's what are called kind of economies of scale as we start making more and more things. The subsequent ones are cheaper to make than the previous ones. And so as we go through those learning curves, we were expecting the costs of a lot of the hydrogen activities and technologies to come down and be cost competitive with existing technologies. That combined with things like tax credits will be very, make a financial sense for the initial offtake. And then the hope is as those start to come off, the markets develop and moves forward, because we're seeing such an emphasis on decarbonization and really the need not just to decarbonize, but also depollute. And so that's where if we can start looking at what we call the hard to decarbonize sectors, then that's where hydrogen can actually make substantial impacts.
Mm-hmm.
And so in terms of the cost analysis and what we've talked about, one way to bring down that cost is to do innovation and to accelerate new designs and new concepts. So work that we're doing within the H2 Nuke DOE consortium at the lab is really focused on, how do we decrease the expensive parts like the catalyst and still maintain the same performance. And so what we're looking at is ways to really bring down the cost by bringing in new types of concepts and new types of materials and really figuring out how to integrate them such that the device at the end of the day is substantially less expensive at full deployment. And this is very much aligned with working with industry partners to understand where they're seeing the issues, where they're seeing the cost drivers, where they're seeing issues of things like Hannah mentioned of being able to operate with renewables. And so how can we start making improvements in these areas? And that's really what's fundamental to kind of our science vision here at the lab.
And I'll just add to that, there are other ways of making hydrogen with low emissions that don't rely on electrolyzers. And there's a lot of work being done on understanding if you can take waste organics and produce hydrogen from it, what is the infrastructure needed to do that? What are the monitoring and metrics needed for that to provide assurance that we understand exactly what's happening to the hydrogen and carbon there? There's also emerging technologies that try to get away from the losses that would happen from the transmission of electricity. If we can be clever about avoiding the losses from the very beginning, that's all going to help the round trip efficiency, as we call it, of taking energy from the sun or the wind and translating that into a usable form with minimum losses.
I've read that another issue that is a big topic right now for some researchers in the hydrogen space is storage materials. As I understand it, there are ways to store hydrogen as of now, but it's quite tricky to store because it is indeed the smallest element in the universe, and it just slips out of cracks that you didn't even know were there. So are either of you involved in any of the research or supporting projects for hydrogen storage to actually get this fuel moved around to where it needs to be?
Yeah, I can take that one. So I've been part of a consortium called Highmark that the DOE funds. And as of this month, we're starting our third phase of that. So it's been running for about 8 years, and we're going to go for another 4 years. The goal of that consortium is to identify novel ways to store hydrogen that lower the energy required to do it and can meet the needs of the end uses. So that group started out really looking at tanks that would go on light duty vehicles, trying to understand how to make them smaller, how to make them store more energy and more hydrogen. And now we're moving away to other applications such as very long-term seasonal storage of renewables or providing energy storage for transporting hydrogen around. One of the key challenges for hydrogen right now related to storage is meeting the time of use and matching it to the source of the hydrogen. Sometimes your wind and your solar is not located where you're going to use the hydrogen.
Right.
You need to transport it. And right now we haven't transported hydrogens at the scale we're talking about in trucks. So we're thinking about other ways to do that, whether it's going to be pipeline or rail. There's all kinds of really interesting technologies being developed. And those can be broken down into the conventional forms of storage, such as you basically have to compress or chill it to increase the density of that hydrogen and make it easier to load it onto a vehicle or load it into a pipeline. Then you have material-based systems where you either create electrochemical bonds that allow you to increase the density of your hydrogen storage, or you actually have materials that have high surface area with chemistries on them that allow you to store the hydrogen. And then finally, you have other solid forms. So you might hear terms such as metal hydrides or metal organic frameworks. These are all emerging technologies that researchers in the US have been looking at and around the world to advance how they perform and start to demonstrate that they can be meeting our needs in the applications that are most relevant.
That's great. It sounds like there's a lot of diverse work happening there. So earlier you mentioned that a big use for hydrogen is in creating metals, making steel in particular. How is it going kind of working with that major industry in trying to use clean hydrogen? Is that going well? Are there any good successes in that area?
There have been a couple really interesting successes in the sense that we're seeing companies come out starting to demonstrate the first ever 100% hydrogen powered direct reduction of iron.
Wow.
And that's the way we need to go, is starting to not just be in the lab and demonstrate the chemistries or the performance there, but really starting to have some de-risking of the industry to get a clear signal on what is needed to be competitive in that landscape. So we're looking at new deployment systems. There's one going on at the National Renewable Energy Lab in Colorado that's going to demonstrate the coupling of this furnace with a hydrogen system and potentially energy storage to understand more about what's going on in that system.
Would that be a zero, like a decarbonized steel manufacturing process, or would it be still partly carbon intensive?
That's a really good question. So, to produce steel product, some carbon is going to be required in that system. So that's understood. However, when we look at the emissions that are resulting from producing iron and steel, it's coming from providing high temperature, high grade heat, as well as providing the reducing agent that goes into taking that iron ore and turning it into an iron sponge that's later processed. So to go from the blast furnaces that use a coke product to a direct reduction iron furnace that uses hydrogen with some source of carbon that might be biochar, it could be biomethane, you can reduce the emissions, the greenhouse gas emissions, by over 95%.
Wow.
So yes, by that answer, it is definitely a form of decarbonizing the iron industry.
Are there sources of clean hydrogen available to companies now? Like if an industrial company wanted to start using clean hydrogen for their power generation or their steel production, are there sources available to them?
Yeah, I mean, so on that, one way that we're looking to develop the marketplace is something called these regional hydrogen hubs. And so one that we're forming in California is the Alliance for Renewable Clean Hydrogen Energy Systems, or ARCHES. And really, there we're looking to match production of hydrogen from clean hydrogen from clean resources, and match that with various demand scenarios. And so that's everything from things like we talked about in the power industry, things that we've talked about within transportation and long haul trucking, but then also around ports as well. And so this is where we see very large pollution burdens that, once again, if we replace those diesel engines with hydrogen fuel cell ones, we can actually make substantial health improvements on these communities. And then eventually, as we establish this marketplace, we can also start thinking about things like airplanes, aviation, airports, and other of these kind of larger sectors to decarbonize. And so really what we're trying to do is bring together all these activities across the state within ARCHES and within that framework to move forward faster.
That's great. Yeah, I can see that when you're trying to switch over these large industries, you kind of need like a matchmaker to bring together like where it could go with the people who are making it. And so I'm glad that there is effort in that space to kind of put these links in place to grow the infrastructure. So that's really cool to hear.
Yeah, and really critical to that is the analysis of the system and analysis of the whole network as a network and as a system. And that's where I think what the hubs are trying to do, and that's really work that Hannah's leading in the hubs as well.
Excellent. So another big topic for hydrogen, which I feel like we kind of have to talk about, are some of the concerns and skepticism about safety and sustainability. Hydrogen is a big topic in the news, partly because there are just so many cool emerging technologies, and also because the current administration is really kind of trying to move the needle forward on green hydrogen. But, there are a lot of headlines saying things like the dirty truth about hydrogen or the myth of green hydrogen. So, here I am with two hydrogen experts. Let's take a few minutes to sort of reality check what the current state is and how safe and environmentally responsible hydrogen really is.
Yeah, so I think if you look at it, the first thing to realize is, like I've mentioned, we've used hydrogen for decades, and we've used hydrogen in very large quantities, typically at refineries and places like that. And so
Right.
we know how to safely store it and safely use it. Some of the largest storage vessels are actually from NASA and storing liquid
Hmm.
hydrogen for, it's used as propulsion for the space shuttles and eventually now for rockets. And so we really know how to do a lot of that already. The key thing is making sure that we're using those lessons learned in some of these other applications. We always are aware of kind of what the safety risks are. As you mentioned, it is a very light molecule, and so it might leak. And so being able to detect those leaks and be able to quantify them and understand what they might be doing, as well as ways to seal them. And there are ways and technologies to do that today that we know how to store it. We use hydrogen, all the time in my lab, and so we also, through the Department of Energy, have a cross-cutting effort on safety of hydrogen in various applications, whether it's pipelines or whether it's just in end-use applications. So it is a concern, but it's definitely addressable. In some ways, we can look at the way we store gasoline on a vehicle now and say, we don't really see the issues there, but we know that there are issues. For example, the way if gasoline leaks, it spreads. Something like hydrogen, if it leaks, it just goes up because it's so buoyant.
Right. And so you're bringing a lot of the knowledge that's already been gained from hydrogen storage when things like if a hydrogen pipeline needs to be built, there's already a lot of knowledge in that space of how to prevent any leaks.
Exactly. We've been doing it for a long time. We should know how to do it.
Yeah, I'll also say that we're approaching hydrogen in a very unique way. We understand that to have a big impact on reaching our climate goals and our energy goals, we need to offset fossil fuel use at large scales. And I think whenever you're proposing large scale infrastructure that's new, you're going to come under a situation where you're going to be having to address and mitigate some of the challenges and risks that arise with such a large infrastructure. And the way we're approaching this is with that understanding, we're working hand in hand with community members, with people who are writing policies around air quality, and we're working to understand what are those constraints where then we can develop and innovate the technologies that can meet those constraints. So we're aware that there are some limitations of hydrogen in the sense of if you're using a pipeline, you have to have the appropriate monitoring technologies in place, or there's a limit to how much you can use your existing infrastructure to deliver hydrogen without coming up to some risks as well. So these are all the kind of considerations we have in analysis. So analysis goes far beyond just cost competitive. It really looks at what are local impacts as well as the global impacts that come from a hydrogen economy.
Right. Now, I understand there are some instances where hydrogen is combusted like a traditional fuel. What are the emissions like when burning hydrogen compared to a fossil fuel?
One of the concerns of if you're burning hydrogen is typically it burns at a higher temperature than, let's say, natural gas. And as you start burning things, you expect higher temperatures, things like nitrogen that gets into the system with the air to make more nitrogen oxides. We've actually developed at this laboratory burners that don't make that true. So these are kind of low swirl burners that actually have been designed for hydrogen use that will limit the amount of NOx being generated. But even more so, even if you just transition a turbine, they have the existing controls to make sure that any NOx emissions to the atmosphere are going to be lower than what they are today or equal to.
Okay, so even when burned, it's better. And with that, we come to one of my favorite parts of the podcast. We have talked about the science, and now let's talk about the scientists themselves. So I'm hoping you can both give me a little bit of the story of how you both got into your current positions and what you love about it.
Sure, I can start. So I did my PhD research in hydrogen. So I've been working in hydrogen for over 20 years. I was initially working during my PhD with a company called International Fuel Cells, which became UTC Power, which became Raytheon. And we were working really, what's interesting about it is these systems, like a fuel cell that generates power, are very complex reactors. And I really really enjoy kind of the complexity of things like transport. How do you get movement of gases in, the gases out, water in and water out? How do the ions and the electrons move in the system? And so I've always really liked looking at that aspect of it, and really kind of imagining myself as one of these little ions that's moving through all these little domains. And what do I do when I see kind of catalyst particles and things that I want to bond to or not bond to? And so that's always been a source of fun for me. And so all of my research now is looking at fuel cell or fuel cell like systems, whether that's CO2 reduction, whether that's water electrolysis, which is kind of the opposite of the fuel cell, where you're generating hydrogen, oxygen, like we talked about. And so that's really focused where I am. Then after my PhD, I kind of joined the National Laboratory and kind of worked my way through the ranks to where now I have a group of researchers that are all focused on different aspects of kind of these technologies.
What's the most fun thing you get to do on a semi-regular basis that maybe people wouldn't expect you get to do in the lab?
That's an interesting question. I mean, some of the most fun stuff I do is probably actually talking to students and other junior researchers, and kind of seeing their ideas and helping them realize kind of their ideas into practice. There's some really cool experiments that we get to do, whether it's at things like the user facilities. So these are giant resources that are funded by DOE, like giant X-ray synchrotrons, as well as playing with things and techniques like being able to analyze how much gold is in a material, which we could do. We're not supposed to, but we might toss jewelry in there and things like that sometimes. And so there are a lot of fun things that we can do kind of around the hydrogen ecosystem, and really exploring the transport and processes.
Great. And Hannah, what about for you? How did you get into your current role?
I got started in science when I was a kid rollerblading around the basement of a laboratory while my dad finished his experiments. And he introduced me to the scientific method right from the get-go. And I really followed that path, starting actually in material science. And I was really interested in nanomaterials were the hot thing at the time. There were a lot of questions around what they could do. And I heard a talk someone gave from the environmental engineering department about the effects humanity have on ecosystems. And it just was like love at first sight. I really got so interested in that bigger picture connection of what things do at the broader scales. I worked in a biofuel research lab after that to get into energy systems for the first time. I really loved that application. But again, I found myself really craving to understand to what effect does a new way to break down materials lead to an impact at the broader scales or deployment of technology. And from there, I did my PhD work, and following that, looking at the broader picture impacts and economic impacts of technologies, ranging from bioenergy to moving into hydrogen. And I've kind of come full circle because now I work with material scientists again, looking at materials for hydrogen storage. And so I really feel like I've found my happy place because I love the details. I love understanding the chemistry. But I also feel like I play a very helpful influencer role, unfortunately, I should say that term, but an influencer role in helping to guide what the research is doing and communicate the value of innovation to people who might just want a solution today. So that's something that came up recently with the Nobel Prizes that just were delivered, is discovery science is still so important. We talk about needing solutions to climate change today, but we also need discovery science to help us figure out things about the world that we would never just find if we were on a straight course trying to answer one question or solve one problem. And so I feel like I get to play in both of those applied science and discovery science zones, and that makes me so happy.
That's awesome. It sounds, by both of your descriptions, it sounds like a great field to work in. Okay, well, I think I've taken enough time away from these busy scientists. Thank you both so much for being here.
Thanks for having me.
Yeah, thanks. Anytime. Thanks so much for tuning in to A Day in the Half-Life,
amidst your many options of amazing science podcasts. And I know you've heard this before, but if you have a second, please like and subscribe on your listening platform of choice to help us get more awesome, science-hungry listeners like yourself.